Okay, so we're going to compute a limit with fractions. The natural thing to do here is to find a common denominator for the two fractions on top. So a common denominator that always works is simply the product of the two individual denominators, so 2 times 2 minus x. So I'll just multiplied the top and bottom of the first fraction by 2, and multiplied the top and bottom of the second fraction by 2 minus x. Of course, we should always let our grader know that we try to evaluate the limit directly, and here we get 0 over 0, so it's indeterminate, hence the need for the algebra that follows. Now that we have a common denominator, we're ready to add the two fractions. I distributed the 7 to the parentheses. So dividing by x minus 4 is the same thing as multiplying by its reciprocal. 7 is a common factor in the numerator, so we factor that out. And we anticipate a cancellation of that x minus 4 in the denominator, the thing that went to 0, with something in the numerator, but 4 minus x is not exactly the same thing as x minus 4. In fact, they're just negatives of one another, right? So we factor out a negative 1 from the in the numerator. So now we see that we have x minus 4 as a factor in the numerator and denominator, hence we get a cancellation. Yeah. X minus 4 divided by x minus 4 is 1. And we get our final result by evaluating directly. X goes to 4. Anyway, so that's a common type of question. Limit with fractions, find a common denominator. Things should cancel. Evaluate directly. We're going to do a second limit problem, this time one involving a square root and polynomial. We're evaluating directly in case we don't get an indeterminate form, but behold, we do get an indeterminate form, and letting our grader know that we realize that. So we know that when we have a square root, we should think about multiplying by the conjugate of the factor involving the square root, because that's going to force a difference of 2 squares. And when you square the square root, it gets rid of it. And we're going to multiply the top and bottom by that conjugate. So again, multiplying conjugates gives you a difference of squares. Hence, we get rid of the square root. Now we're simply going to leave the factor, that conjugate, alone in the denominator, because we anticipate that we're going to, when evaluating the limit directly as x goes to 3, that factor, square root of 3x plus 5, then plus 2, will be not 0, right? So it'll be non-problematic, so to speak. I'm also factoring the x squared minus 9, that's the difference of squares, because maybe you can see that we are going to get a cancellation after we factor out a 3 in the numerator. So x minus 3 divided by x minus 3 is 1. And now we can evaluate directly, and we get a very determinate number, 1 over 8. And that is the limit. So when you see a square root in a limit problem and you get indeterminate form, think about multiplying by the conjugate of the factor involving the square root.
All right, so we also have, what section did you have those special trig limits? So derivative of functions. That was like a 3.3, but we might as, since we're computing limits, we might as look at the special trig limits, right? The ones we can use instead of L'Hopital's rule. All right. So do we recall what this limit is? something goes to 0 here, and we have sine of that thing divided by that thing. Right? That's equal to 1. That's one of our special trig limits. Yeah. Right, and the important thing is to notice that, I mean, the thing that's inside of sine could be complicated function of x or whatever, but as long as that thing goes to 0, that's inside the sine, and the denominator is exactly the same as what's inside the sine function, then we have the special trig limit. Okay? Things to notice are that the limit of this of u, sine over u, we know that that's also equal to 1 just by the limit rules, right? We know that we can think of that as 1 over sine u over u. Reciprocal of reciprocal, right? And now by our limit rules, we can just take the limit of the top and the bottom, as long as the bottom doesn't go to 0, obviously. But by our special trig limit, it doesn't. We just get 1 over 1. Okay. So that's also good to notice that even if the sign is in the denominator, as long as you somehow force the argument of our sine function in the numerator, we still have our special trig limit. Okay. So let us start. Okay. So this is an example. That's pretty kind of comprehensive, I suppose, for the special trig limit. Well, never mind, it's not comprehensive. It's just a standard example. So if we evaluate directly, of course, we get tangent of 0 plus 0 over sine of 0. So that's indeterminate. And we can't use L'Hopital's rule yet, if you know it. So we're going to have to, seeing that we have sine and tangent, which can be written in terms of sine and cosine, we're going to force our special trig limit in there. Okay. So the first thing to do is restate tangent as sine over cosine. Okay. Why is this cosine not a problem, right? Well, it's not a problem because cosine at 0 is 1. So that's all right.
What did you do with the sine of u by u? Like, I didn't understand that.
Okay. So can anybody suggest what the next thing to do might be if we know that we're going to use our special trig limit here? Anybody? All right, okay. So
we add sine 3x from cos 3x and 5x.
yeah, so we're going to just divide by both top and bottom by x, right? Or if you'd like, we can maybe, what would we like to see for the first term over here? What would we like to see in the denominator so that we have our special trig limit? We would love to see 3x, right? Exactly the thing that's inside sine. But of course, we need to multiply the top and bottom by 3x, right? It's a way of multiplying by 1, and therefore not changing anything. One of the most powerful two tools, right? Multiply by 1 or add 0 in math. So. Okay. And then the denominator, let's think of it this way. We want to see a 4x. So we're going to introduce the 4x in the denominator and extroduce it out of the numerator. All right. So now we can kind of factor out an x. Yeah, I would have thought of this as like dividing the top and bottom by x, but that's fine. Right? It's like algebra is like folding laundry. There's more than one way to do it, and it's about as much fun. So unless you enjoy folding laundry. So, right? So yeah, we're going to factor out an x. from top and bottom. So x on top, and what's left behind, we're going to think of this as 1 over cosine 3x. Right, we're just kind of regrouping so it's obvious where the special trig limit applies. And yes, we're left with a 3, thank you. Well, we're not using quotient rule because we're not differentiating, right? We're just computing a limit. Somebody asked in chat, well, something about quotient rule. Well, that's not relevant here. We're not differentiating anything, right? And then we're left with the 5. Right, I factor it in. On bottom, we factor out an x, 4x, I should say. Okay. I could have factored out. Yeah, that's fine. All right, so are we now ready to take a limit, right? Yeah, I mean, I'm not exactly sure what they require in the exam. Since you're just learning the limit rules, right, or you're being tested on them, okay, these cancel. So I don't know if you have to make a precise statement like limit rule says that this is the same as. Maybe you can tell me, right? So the limit as x goes to 0, and then you can just take the limit of each factor, right? Times limit x goes to 0. Plus the limit of a constant. Okay, divided by, and then we have in the denominator, we have the limit of a constant. Jeez. These limit rules, I forget how tedious they can be to demonstrate to your grader. Right, so that's just all the limit rules. So here we get, for the first factor, we get a cosine of 0 is 1, so we're left with a 3. Our special trig limit tells us that this is equal to 1, so times 1. And the limit of a constant is a constant, right? A constant doesn't care what x does or doesn't do, it just remains itself. And then we get 4 times, and special trig limit is 1. Right? Anyway, yeah, we get 2. How exciting. So, all right.
Is this going to be recorded?
Something's wrong?
No, just figuring stuff out.
Is there going to be recorded?
Why is there?
Yeah, it's being recorded.
Why is there a limit x approaches 0 at the second last step where you're taking the individual limits?
Can you repeat the question?
All right. So after you crossed out the x's,
Yes.
Why does the next step have a limit x equals to 0 on the left?
Oh, yeah, you're right. Yeah, okay, whatever. So I was started writing out limit, right? But then I said I'm gonna use the limit rules. But you're right, the limit, right? I'm just now using the rules, so the limit statement goes for each individual factor, each individual term, numerator, denominator. Thank you. Good point.
I have a question.
Yes.
When you factored out x on the numerator and got 3 over cosine 3x times sine 3x for 3x, why wouldn't you just factor out a 3x?
That's because there's another term in the numerator with a 5. Right? Do you see? So yeah, I mean, you're right. If I had like 6x for the second term, I would have factored out a 3 maybe. But yeah, I wasn't sure what I was going to do, but didn't. Right. Yes.
You know what happens if we use hospital rule on the test?
Well, hopefully, I mean, use it to check, right? Obviously, you can check using it, but hopefully your grader wouldn't give you credit if they explicitly said don't use it, right? I mean, that's only fair, I think. So, yeah.
When we had like sine over 3x over cosine 3x plus 5 all over at sine 4, you just
Very good point. Yeah, that's an absolutely valid strategy. I didn't think about it, but yes, right? So the suggestion is that over here, since we have a single term in the denominator, we can write that as two separate fractions, right? So we can think of this as tangent of 3x over sine of 4x, right? In a sense, this is a little bit more elegant, it seems to me, so very good, right? And then the limit rules, we can just take the limit of each term individually and just think of this as 1 over cosine 3x, sine 3x, and then sine 4x in the denominator. Right, so then we introduce a 3x here, 4x there, and then of course we got to introduce that out to keep everything same. But absolutely very good. Yeah, I like it. So then we have introduce a 4 on top and bottom. And if we get a different number here, I'll be ashamed, but you know. So you get 1 at the limit, 1. This is 1, and this is 3/4 plus 5/4. So that's 8/4. So very good. That's still 2. So I'm happy about that. Okay. All right. Let's do another one. All right. Just to quickly mention it. So what question is this? Was that only number 3? Oh my goodness, right. Number 4? All right, so how would we, using our special trig limit, what do we have to do? Yeah. I know this is, again, kind of basic, but, you know, the rule is that you want to keep it simple.
I mean, math exam probably won't be.
Maybe it will be, you know?
I've known everything in a college math exam before.
Oh, yeah, I forget that some of you are probably like first semester college students. That's crazy. That's insane to me. All right. All right, so what do we do? Yeah, we can factor out so we noticed that, and by the way, we get 0 over 0 if you evaluate directly, right? So yeah, we can factor the numerator, or the argument of the sign, rather, I should say, right? And then we're just going to think of this as a product of two fractions, because using our special trig limits, right, we have to introduce to various things here. So what do we want to introduce in the
What's that symbol?
Can you ask that again?
What's that symbol about the equal sign?
Oh, yeah, sorry about that. That's 0 over 0. I was,
Okay.
because I said, you know, you want to make a habit of trying to evaluate the limit, demonstrate to the grader that you notice that that's an indeterminate form, and I forgot to do that, but so I was writing 0 over 0. All right. Okay, well, what do we want to see for the second factor? What do we want to see on top over yonder? Right? But we want to see exactly what's inside our sine function. So we're going to introduce that. Yeah, and if anybody's thinking of doing something like sine of x squared minus 4, I don't know how somebody wanted to split it. Oh, yeah. So sine of a times b, I hope you know, is not the same thing as sine a. I won't even justify that with an equal symbol there. This is, yeah. right? So sine of A times B is not the same thing as sine A times sine B. So somebody wanted to know whether we can express this sine of the first factor times sine of the second factor. So here.
That'll be too easy.
Okay, so we're going to introduce an x minus 2 here. And so, of course, we're going to extraduce it out over here as well. So that way we're just multiplying by a form of 1. But then we also need something in the bottom, right, for the first term. It's not quite complete, right? We have to see exactly what's inside our sine function on the bottom. So we're going to also need to introduce an x minus 2. Sorry, x plus 2, I misspoke. Okay, that's in the denominator, so I'll go ahead and introduce that term in the numerator. Okay. All right, so then, right, yeah, so I don't know how formal they want to be. Unfortunately, I haven't taken calculus exam in over 20 years, so I don't know the trends, but, right, in class, did they ask you to do like a formal substitution here? Like, I'll show you what I mean.
I will. They had on our notes, yes.
So you might have to be really, really careful here, right? Because they want you to say, I'll do one of these more formally. Okay, so that's just limit rules, right? So we know that this will go to 1. Okay, and so will this, and this will go to 4. So you get 1 times 1 times 4. But I want to ask your professors whether, if you're taking something like this, do you have to say, let u equal to x minus 2?
No.
Do you see what I'm saying?
I just have to substitute. Like in our notes, we just substitute with you.
Okay.
Our teacher told us to do that.
To do it?
Yeah.
Okay. So then we note that as x goes to 2, right? Obviously u will go to 0. Okay. So then you do the formal substitution to say that x goes to 2 is equivalent to saying that u goes to 0. Or I should say if and only u, I suppose. So then you get u over sine u. And to get it in the form that is boxed in your textbook, so you get sine of u over u, right? We just rewrite that fraction as the reciprocal of its reciprocal. Use limit rules. So you get 1 over 1. So something like that. You might want to ask your professors how formal you got to be. You have to be.
Is it? Should we?
All right. And one more, because I believe there's usually another special trig limit that you use. Do you remember what it is?
Cosine of theta minus 1 over. Sorry.
Yeah, I think so. So I forget what it is exactly. But I know that this problem has it. So this is problem number 5. I'll make it a little bit more abstract. Let's put an A in there, right? Oops. I meant minus, not plus. Multiplying by 1 is a lifesaver. And adding 0 is another lifesaver. But adding 0 somehow works better in integral calculus. Okay. But you guys don't know. All right. So evaluate directly, we get 1 minus cosine of 0 is 1, so we get 0 over 0 there in determinant. So we're going to do some sort of, right, the other special trig limit is, of course, 1 minus cosine of theta, say. over theta as theta goes to 0 is 0. Okay. So that's another special trig limit. All right, so I'm going to try to use that. I mean, we're almost there. And so I'm going to think of it this way, but what's the problem there, right? Is that if I use, so if I multiply the top and the bottom by a over here, okay, and I try to evaluate the limits here, the first factor would go to 0. The second factor, however, would go to 1 over 0, so that would be plus or minus infinity, right? So, and 0 times infinity, is that any kind of arithmetic we know how to deal with? You know, not with, it's not like the arithmetic of the numbers, right? It's really a limit thing, so this is still indeterminate. All right. So 0 times infinity is indeterminate. So what do you suggest we can do? I didn't even look at this ahead, man. So I think I'm just going to do the following. I'm just going to force the difference of squares. Do you see why? I'm going to multiply by the conjugate. Does anybody see why I would want to do that? So multiplying by a formula 1. Right, well, you know that we multiply by conjugates when we have square roots to get rid of them, but there's another reason to multiply by conjugate, right? It's in order to take advantage of certain Pythagorean trig identities. So, for example, sine squared, we know, is 1 minus cosine squared. And that's a difference of squares, so we know that can be factored into conjugates. Okay. So another time you can multiply the conjugate is if you see that that'll give you a certain trig identity. We can simplify by using, let's say, Pythagorean trig identity, right? And I don't have information about how many questions on your exam or anything, but maybe chat will know better, or your professors, obviously. All right, so multiplying the numerators there, we get conjugates. Product gives you difference of squares. I'm not going to bother multiplying denominators. Okay. Right, so you see the idea there. We get 1 minus cosine squared is sine squared. So we've traded in 2 terms for 1, which is nice. And I guess I didn't get to use the other special trig limit after all, unfortunately. Okay. Right, but what do we, to use our special trig limit over here, we can think of that as sine of ax divided by x, right? Quantity squared, so properties of exponents. And then we want to introduce a in the denominator, and then of course extroduce it out in the numerator. Right, so we get the limit of a constant, so a squared times limit, oh, and x squared is a continuous function, right? So we know we can pull the limit statement inside. That's another limit rule. And then times, I forget how annoying the using the limit rules can be. Whatever, okay. At this point, I think we're just going to be, you pretty much know this, so I'm not going to spend too much time. All right, so we get limit of a constant is a constant. This gives us our special trig limit. We should say that as x goes to 0, so that is a times x. So you could formally maybe call that u or something. I'm like working a problem backwards. So note that as x goes to 0, u goes to 0. So we get our special trigs. Alright. And then here we just get 1 plus 1. So the answer is a squared divided by 2. All right, beautiful. Well, I think
Excuse me?
yes.
So how do you get the limit as a of x equals 0? Can you explain that again?
The limit as what approaches 0?
A times x approaches 0.
Oh, yeah. So what I was attempting to say is that we have this limit, x goes to 0, we have sine ax over ax, right? But technically, if we have sine u, we need u to go to 0. So it's silly, but here we have ax, but it's only x that goes to 0. But I just noted that if x goes to 0, then so does a number times x. That way we have exact, like if you let u equal ax, then you can use that special trig.
Okay, thank you.
I think that's enough of those special trig limits though, so let's move on. What's next? Do you guys want to do epsilon-delta? Because that's the best, right? So how many Greek letters do we know by now? What?
Too many.
Too many? So epsilon, the alpha, beta, gamma, delta, epsilon,
Omega.
theta, omega, phi, pi. Okay. Anyway, epsilon delta. And here's my prompt for epsilon delta problem. So, all right. So we know that there's a precise limit, definition of a limit using epsilon delta. So this is the epsilon delta definition of limit. Okay. And it goes, so if you have a limit statement, limit as x goes to some number, a, of some function, f of x, is equal to L. So has everybody memorized this definition like it was like a short poem or something? Yeah, sure. It's like you can write it in lines, right? So, yeah, so for every delta, which is a positive because it's a distance, there exists, sorry for my handwriting, there exists a delta, which is a distance, so it's positive, such that the following condition holds, right? For any x in the domain of your function, maybe I should write that, maybe not, that's ask your professor, but for x is in the domain of your function, we have that the distance, right? So the absolute value is, or the mature way to read that is distance, right? The distance between your function at x minus the supposed limit is small, it's epsilon small, whenever x is close enough to a. Right? Delta. Okay. So this is our definition there, formal definition. And it's just saying, look, x is getting close to a, right? So how close? Well, delta close. The distance between x and a is less than delta. And if that's the case, then we're guaranteed that if you take that x and you plug it into your function, the value you get is going to be close enough to the supposed limit, right? L, epsilon close. So x gets close to a, therefore f of x should get close to the limit. Delta is the distance we associate with the x-axis, if you will, and epsilon is the distance we associate with the y-axis. All right, so let's go ahead and make up a problem here.
Wait, which one was the x-axis, the y-axis?
Well, yeah. So we associate. This is this is the x-axis. This would be a plus delta. This would be a minus delta, and we're saying that x is the distance between x and a is less than delta. So delta is the distance we associate with the x-axis. You know, d is before e in the alphabet. Delta comes before epsilon. X comes before y. And then, right, if you have, oops, I messed up. Yeah, eraser. And the epsilon is the distance we associate with the y-axis, right? So you have L, and then this would be L plus some distance, epsilon. This would be L minus some distance, the same distance, epsilon. Right? And we're just saying that f of x, once we plug x into our function, our f of x should be within a distance of epsilon of the limit. Anyway, delta, x-axis, epsilon, y-axis. All right, so I believe we're on question number 6, right? This is for my sake. Okay, and if you are going to be writing out the definition of the epsilon delta on the exam, maybe you should say for x's in the domain of your function. For all x's in the domain. Okay, I'm a little worried that I'm leaving out the detail. All right, so let's give me your favorite line equation.
3x plus 3.
3x plus 3 is a beautiful function.
Let's put a little let's differentiate a little. Put 3x plus 4.
All right. Well, sure. So plus 1, right? And let's let x approach a negative value like. So what do you want it to be? -1 or? Yeah, no, okay, -1. So what is this limit? No, it would be 1 because we changed it. I don't like it. So I hope nobody's taking notes or stuff like that. Like, not yet. Okay, I'll make it up because 3x and let's say 2, so minus 2, 10. X is going to go to -2. How about that? There you go. Okay, good. So we know this limit is 4, right? Because we just evaluated correctly. All right, so we might as well identify what is x approaching. So in our limit statement, we see the generic thing we use there is a. So x is approaching a. So a must be -2. All right. Our function is 3x plus 10. And our limit is 4. Okay. And now we'll do the crux of the problem is to, given an arbitrary epsilon, they can give you a number or they just use the symbol epsilon, show that a delta exists, right? And it's a delta to satisfy some conditions. So the crux of the problem is, given epsilon, you have to define delta. So what we're going to do is write down the 2 inequalities here that kind of give you the criteria for how delta should be defined. Right? Okay, so we have one inequality. Oops, I almost forgot something. Why is that 0 over there in the definition important? Okay, let me make sure I emphasize that. Why is the 0? Why does the distance between x and a have to be more than 0? Well, no, it doesn't matter. If I say that the absolute value is there because it's a distance. The distance is positive. But It's just that with limits, right, we only care how a function behaves around A. We don't care what the function does at A, right? So limit is like anticipation. What the function does at A is like culmination, right? Okay. So limits, they don't tell you what a function does at A, but merely to tell you how a function behaves around A. So we don't care when x is equal to A. So if x were A, then A minus A would be 0. So this is a way of saying a deleted neighborhood around A, right? We don't care what happens when x is A with a limit. Okay. Yeah, I'm glad I caught that. Yeah, again, the absolute values, because we're looking at the distance between x and A. The greater than 0 is because we don't care what happens when x equals A with the limit. I'm answering some chat questions. All right. All right, so let's write down these two inequalities. So we have, we're going to have that x is close to A. So x minus A should be less than delta. So, and then the function at x, we know that that's, what is it? It's 3x plus 10. Minus the supposed limit, which is 4, should be less than epsilon, right? So over here, we're gonna, I only care about it, really the one side of that inequality. Okay, and over here we simplify. Okay. Right, and if you do things correctly, with this inequality that the absolute value of f of x minus L is less than epsilon, if you do things correctly, you factor, one of the factors you have to see is this. So notice that we can factor out a 3. Okay, and the absolute value of 3 is 3. Divide both sides by this positive 3, so the ordering doesn't flip. So can you suggest, by comparing the two limit statements after we did some algebra there, can you suggest a way to define delta in terms of epsilon?
Delta is less than epsilon divided by 3.
Yeah. Yeah, comparing this delta to this, right, these two inequalities, we should let delta equal epsilon over 3. Okay. By the way, anytime you have a line, does anybody know the shortcut or the hack to defining delta in terms of epsilon? So if you have limit as x approaches A, and you have just some generic line-looking thing, right? Do you know, given epsilon, the formula for defining a sufficiently small delta? It's going to be epsilon over the absolute value of the slope. Okay? So that's a way to check yourself if you have a line. Indeed, right? What's the slope of our line? 3. That's right. So we define delta to be epsilon over the absolute value of 3, which is 3. Okay. All right, so that's a chunk of the credit for that kind of problem. They used to make you actually then prove it using the definition. And if you want to kind of formally state, if you formally want to prove it, sorry, I don't know where. Oh, there. You just use the definition as a template. I'm just going to copy something real quick. Whatever. Thank you. All right. So I'm going to use this as a template for a more formal proof. Right, we're going to, the first line is for every epsilon. So I'm going to, so if I It's like getting a Shakespeare play and all the lines are numbered. Okay. So the first line to take care of that one, we're just going to say take an arbitrary epsilon. Because we want to prove something for any positive quantity, so we're just going to take an arbitrary positive quantity, assume nothing about it that's positive. And the second line is that we have to show that there exists a delta. Well, we did all the work. We're going to poof delta into existence by defining it, right? We're going to say let delta equal epsilon over 3. That was all the hard work. And note that since epsilon is positive, then so is delta. Right, so now we have a delta that exists because we just defined it. And then we're going to take, I guess, take a value of x in the domain of the function. This is a detail. I don't know how much we have to worry about that. Okay, and then the fourth thing is that it's the nature of an implication, right? We're saying that this must be true if this were true. In the case that it is, we're not saying it is or isn't, but if it were true, then this must follow. So we assume, like hypothetically, that this is true. So you say, suppose x minus a, so x plus 2, is less than delta, right? And then we want to finally show that this inequality, that's number 5, will necessarily follow. So we'll say consider f of x minus the supposed limit. Okay. And then you just restate all your work. Okay. So we simplify. It's taking too long. Okay. And then reason that, okay, well, we assumed that the absolute value of x plus 2 is smaller than delta, right? So what we can leave the 3 alone, but replace this factor with something which is known to be a bigger factor, namely delta, or assumed to be a bigger factor. So the whole product is bigger. Okay, and then you say that delta we define to be epsilon over 3. You have a cancellation, and there you go. That's it. If you follow this chain of equalities and inequalities, we see that the absolute value of our function minus the limit is eventually smaller than epsilon. And that's what we wanted to prove. Okay?
Great.
Hi, there's actually a few questions in the chat about the epsilon delta definition.
Oh yeah, so this would be the maximal value. This delta. In other words, we can choose delta to be smaller than that, so we can make delta epsilon over divided by 10, right? It would still work. It still would work. So if we let delta equal epsilon over 10, then over here we would just write 3 times epsilon over 10, which is 3/10 of epsilon, which is obviously going to be smaller than 1 times epsilon, right? So that's a smaller delta would work, but we couldn't define delta to be anything bigger than epsilon over 3. So epsilon divided by 2 would not work. So that's so the reason they say this because some students are really clever, and if they know that you can use a smaller delta than what we found here, they'll just say let delta be epsilon over 1,000,000, and it's probably not wrong, right? We see the problem with it, so they have to say maximal delta, so that students don't do that. Okay, does that make sense? All right. I think. So maybe, do you guys want to do an epsilon delta for an infinite limit? Maybe we should, right? So one more epsilon delta. All right, let's do this. So this problem would be number, I forget this doesn't know. Yeah. All right, so now we're going to define an infinite limit. So
Wait a
this,
second, could you scroll up by 2 seconds?
yeah. Oh, how far?
Just to the proof. Thank you.
So infinite limit. So limit as x approaches a number of a function is equal to, let's say, plus infinity, right? You can easily also do the minus infinity, but graphically, what would that look? What would the graph of the function look like around A? Would be a vertical asymptote. We know that, remember, what defines a vertical asymptote in calculus? If at least one of the one-sided limits is an infinite limit, so plus or minus infinity, right? So that would look like the graph around A of our function would look like what would be a vertical asymptote. Okay, but we know that what this means is that for, instead of epsilon, we're going to say for any number, m, could be positive, doesn't have to, you don't have to specify it's positive, but for all m, we know that if we can get x close enough to A, so delta close, so there must exist a delta, which is a positive quantity, it's a distance around A, such that for all x in the domain of the function, right, so that excludes x equals, that would exclude x equals A. So, that your function will exceed this arbitrary number m whenever x is close enough to A. Right? So delta close, and it's a limit. So x, we don't care what happens when x is A. But you see how this works, right? M is any number, so you can make it as large as you want. So you could have m1, and then m2, and so on and so forth. But the idea is that since m2 is any number, make it as large as possible, we're saying that as long as we can get close, x gets close enough to A, and we plug that x into our function, we're going to get that f of x exceeds that arbitrary value of m. Right, so that kind of forces the function to go off to infinity. Okay, that's a terrible picture. All right, so let's do an example. Let's suppose we take the limit as x goes to 5. Let's say 4 over x minus 5 to the power of 4. Well, that doubles. Now, this is clearly going to be positive infinity because we get 4 over something that goes to 0, but from the positive side, right? As x goes to 5, x minus 5 goes to 0. And it doesn't matter from which side because we're taking this thing that approaches 0 and raising it to an even power. So that would be 4 over a positive 0, so to speak. So that's positive infinity, right? By the way, there's a sign-in sheet going around. So if anybody that came in late, does anybody see what the sign-in sheet is? I'll just put it at the exit door, if in case you need to leave. All right. All right, I'm back. So, okay. Right, so we're going to write out the two inequalities, right? So we have to have that our function. So if x is close enough to 5, so the absolute value of x minus 5 is less than delta, it's positive, then we would want the function, the distance between the function, its value, and the supposed, well, sorry, we want the function to be bigger than n, so I apologize. Let's clean that up. So we want our function to be bigger than m for this arbitrary m. Right? So does anybody see how to manipulate one of these inequalities so that we can define delta in an appropriate way? Well, here, let's assume m is positive. Right, so we can divide both sides by m. Right? Okay, and then we can multiply both sides by x minus 5 to the power 4. And so let me rewrite it like so as well. So it's, if you're used to reading from left to right, maybe that's more legible for you. All right, so then what can we do to, something is this, 5. Okay. All right, so what's the next step, do you think?
Take the fourth root of both sides.
That's right. Right, because we want to, again, this is what we're aiming for. We want to see x minus 5, or rather the absolute value of x minus 5. So we're just going to take the fourth root of both sides. And by the way, in general, what's the square root of something squared? What's the most general statement you can make? Absolute value. Absolutely true. Right? And so if you have, likewise, right, if you have the fourth root of something to the power 4, you're going to get the absolute. You're going to get the absolute value of it, right? Because raising the x minus 5 to the even power makes the result positive, so it didn't matter whether the original was positive or not. We didn't know, but the fourth root then is guaranteed to be non-negative, so we need to put an absolute value. All right. Anyway, so taking the fourth root of both sides. We have to make sure that we know that on the left we get the absolute value of x minus 5. And here it is what it is. I don't know what that is. So that would be square root of 2 divided by m to the 4th power. But anyway, now we know how to define delta. Right? By comparing this inequality to that one after we manipulate it, we see that delta should be defined as the square root of 2 over m to the power 4. Okay. I'm not going to go through this, but it's just a way to, what's a good way to find it. Same procedure, write down the two inequalities, right? Manipulate this one until you can say something about that other one. Yes?
So how does that function equal infinity, guys?
Well, the function doesn't equal infinity. The function is undefined at 5. It's the function that grows without bound. It explodes, right, as x approaches a. So we can't talk about what was your question again? Second.
Why does x equals 5? Why is the function infinity?
Oh, because you get a non-zero number over 0. That's slightly positive. So, right, right, if you have a non-zero number divided by something that goes to 0, you're going to get plus or minus infinity. You just have to know whether it's plus or minus. But we can go over that as well.
I have a question. So why couldn't we just leave the delta function, like delta is less than the fourth root of 4 divided by n?
We could have. That's not a problem. I don't know. Maybe I was trying to secretly impress the universe by knowing what the fourth root of square root of 4 is. But, All right.
So,
All right. We need to get going here, right? All right. So before we talk about continuity, maybe we should talk about asymptotes. How about that? All right, so how do we define horizontal asymptotes? Yeah, derivatives are on the exam. All the way through section 3.3, including quotient rule and product rule. So yeah, derivatives are on the exam.
Is chain rule on the exam?
That's a good question. I don't believe so, but maybe you guys can tell me better because that's not in, that's like section 3.4 or something like that. So I would believe it's not on the exam. Double check with your professors. All right, horizontal asymptotes. The note from the coordinator of 2413 said it's only through section 3.3. Right, so how many different horizontal asymptotes could a function have? 0, 1, or 2, right? Okay. So horizontal asymptotes are simply tell you what value a function approaches as x either goes to infinity or negative infinity. So it's the long-term behavior of the function. As x gets large or as x gets very negative. So we have to, whenever they ask us to find horizontal asymptotes, we have to compute the limits. Two infinite limits. Limit as x goes to infinity of your function. And if that limit is a number, right, you get a finite number, then we can say that the function in the long run approaches the horizontal line y equals L. So that would be a horizontal asymptote. If the limit doesn't exist, then you don't have that one. But of course, we can have that the asymptotic or limiting behavior of the function as x goes to negative infinity might be different than how the function behaves as x goes to positive infinity. So we could possibly get a different number, or it could be the same, or it could just the limit could not exist. Let's call it m, right? And then there, if you have a finite number m, then that's another horizontal asymptote. Yeah, if you're stressed about the chain rule, well, not for the exam, but I think you heard the Texas chain rule massacre. Well, it's going to be an exam too. I'm just joking. Okay, that's a.
I mean, that's what's going to happen to most people's grades if chain rule comes on the exam right now.
That's an old joke, by the way.
Why?
Texas chain rule massacre. All right. So do you guys remember how you deal with if you have a polynomial over polynomial and you want to find horizontal asymptotes? Right. So if you have like 5x cubed, always pick a silly prime number, minus x squared plus 1, right? And that's over 3x plus x squared minus x cubed. Okay, well, so not the way you did it in pre-calculus, right? But rather, how are we going to do this in calculus to find horizontal asymptotes, if any? Yeah, so we know that we have to take two limits, infinite limits, right? Not infinite, but limits at infinity. So as x goes to plus infinity first, let's say. And since we can't use L'Hopital's rule on this test, we are just going to look for the highest power of x somewhere. Let's say the denominator. Let's make that a rule, right? So look for the highest power of x, so that's x cubed, and then just divide the top and bottom by x cubed. And of course, I'm very safe in dividing by x cubed because x is not 0, right? I mean, x is going to infinity, so x won't be 0. So you're going to divide the top and the bottom by x cubed, highest power. Okay. So then this allows us to divide each term in the numerator by x cubed, giving us a constant x over x squared, x over x cubed. That simplifies, let's not be silly. X squared over x cubed is 1 over x. All right, and then we have 1 over x cubed. Now, can anybody maybe tell me like what the motivation for this is? Like, what's the reasoning for doing this?
1 over x and 1 over x cubed will go 0.
Yeah, that's right. So if you divide by the highest power of x on top and bottom, you'll just be left with constants, which don't care what x does or doesn't do. So at the limit, they'll be the constant. And then you'll have some number over something that goes to infinity, right? So the limit, so if you have a number over some positive power of x, maybe I should say it's rational or something, but whatever. So as x goes to plus or minus infinity, you should know that this is 0, right? So that's what we're taking advantage of, together with the fact that the limit of a constant is constant. So that's what we're taking advantage of when dividing by the highest power of x. So now using limit rules, I won't write it, but the limit of a constant is equal to constant. This goes to 0. I should maybe write it like that. This will go to 0, and so on and so forth. And then the constant is right? So you're going to end up with 5 over negative 1. So that's a finite number. So indeed, in the long run, as x goes to infinity, our function approaches the line y equals negative 5. Right? So that's a horizontal asymptote. Yeah. Yes, this should be x squared. Thank you. All right, but are we done? Well, no. Never forget to check the other, the other long-term behavior. So let's suppose x goes to negative infinity. However, nothing will change here, would it? Right? Because we would still, it's a limit at infinity, so we'd still divide by the highest power of x. So x cubed, we would still simplify and take the limit, take advantage of our special limit there. And you would still get negative 5. Right? Negative. So that's a horizontal asymptote. Okay. Let's do something a little bit more tricky. So maybe we should do this one. Maybe I'll involve. Does anybody know the limiting behavior, the arctangent? Does anybody know the graph of arctangent? Yeah, you should know it, right? It looks something like that. So as x goes to infinity, arctangent approaches a horizontal line, namely y equals pi over 2. And as x goes to negative infinity, arctangent of x goes to negative, approaches the line negative pi over 2, y equals negative pi over 2. So you want to know those. Of course, there's other things you want to know, like the limiting behavior of an exponential function. Is that pi over 2? Yeah. Right. All right, so, and also inverse or arctangent at 0 and 0, right? All right. So somebody asked me to do a limit. I don't want to do that one, not yet. All right, so find horizontal asymptotes, if any, of arctangent of, let's say, 12x squared plus 1, because who cares what that is? And then x minus 2. What do I get? It doesn't make sense. I wrote something And I don't know what it is. 1 second. Oh, okay, 2x. Okay. And let's use this. This doesn't matter. Beautiful. All right, so again, horizontal asymptotes, we need to find two limits at infinity. So let's start with the positive version. Okay, so notice that the graph of the arctangent is nice and connected, right? So it's continuous. So we know that one of the limit rules is that you can just consider, you can pull the limit statement inside. And if you get a limit on the inside, then evaluate an arctangent at that limit. And so we're just going to be focusing on that inside, right? So let's just consider this, right? Oops, gotta make that legible, right? So, so what's the highest power of x? Yeah, it's there's an x squared on top, but you're gonna at the end of the day, in the long run, you're gonna be taking a square root, right? So that's like x, but we're gonna look for the say the highest power of x in the denominator, and let's just follow our advice. We said we're gonna divide the top and bottom by the highest power of x in the denominator. Yeah, so the way you're usually introduced to this depends on the professor, right? But some people think of it as, how do we simplify this, right? Okay, so I'm gonna think of it this way. I'm gonna factor out an x squared from the square root, okay? But tell me, when you factor out an x squared from the square root, what should you be writing? You should be writing the absolute value of x, right? Remember, square root of x squared is absolute value of x in general. So in the numerator, I'm going to factor out a x squared, but the square root of x squared is the absolute value of x, and you're dividing that by x. But at the end of the day, inside the square root, we're still left with what we wanted to, which is either constants or constants divided by positive powers of x. And in the numerator, that's pretty easy. Denominator, I meant. All right, so now, what's the definition of the absolute value of x? If you want to trade in the absolute value bars, so to speak, for cases or piecewise function, right? Piecewise defined function. How do you, what's the trade-off here? Right? We know that if x is positive, then the absolute value of x is just x. I mean, x is positive, so you don't need the absolute value bars. But if x is negative, what do we need to do? Well, we need to take this x, which is known to be negative, and negate it. Right? Negating a negative number gives you positive, so has the same effect as taking the absolute value. All right. So now we're going to reason that. Sorry. Since we know that the absolute value of x is just x in this case, since x is positive as x goes to positive infinity, right? So you want to make that statement so that you can then simplify. This is for your grader, not for your sake. So, and then we evaluate this limit. Right, we get that this is 1. Evaluating the limit, we get square root of 12 plus 0 over 0 minus 2. So that is square root of 3, negative square root of 3. All right, so finally, what's the inverse tangent, or arctangent, I should say, of negative square root of 3? Does anybody know? It's like, so square root of 3 over 2, and then
Minus 5 by
1/2, that's square root of 3.
minus 5 by 3.
So the reference angle should be sine of 60, so pi, it'll be 2 pi over 3, right?
Is it acceptable to leave it as
Negative
arctan?
pi over 3, I should say.
Is it acceptable to leave it as arctan?
Oh, I see what you're saying.
That's the simplest form.
Yeah, because it's just a number, right? But maybe, I don't know, it's a great question.
Is it 2 pi over 3 or negative pi over 3?
It's negative pi over 3 because it's tangent of a negative number. Arctangent of a negative number, right? So if we have the argument for our arctangent is negative, then the angle, arctangent always returns a number from negative pi over 2 to pi over 2, right? So the first and fourth quadrant, so to speak, on the unit circle. Okay. Yes?
Why did you jump to the square root, negative square root of 3?
Well, how did I get the negative pi over 3? This is so annoying. You mean here?
Yeah.
Oh, yeah, sorry. Yeah, so square root of 12 over negative 2, you agree with that? So we know that 12 is 4 times 3, and we know square root of 2 is 2. So we had 2 divided by negative 2 is negative 1, so we're left with negative square root of 3. Does that answer the question? Even though it's in a very small font? Okay. All right. Okay. All right, so there we go. We get a finite number, and if you want this, then you just have to know the unit circle well enough, I suppose, and your inverse trig functions and your trig function. So y equals negative pi over 3 is a horizontal asymptote. Okay. Right, and if we stop there and we forgot to take a limit as x goes to negative infinity, then we would have missed half the problem, right? Because there could be possibly a different asymptote, a horizontal asymptote. Okay, and the procedure for taking the limit as x goes to negative infinity is exactly the same. So I'll skip all the details. It's up to a point. Okay. So we would still have, let's say, factor out an x from the x squared from the square root, right? And then we get absolute value of x, and we would have to still factor out an x from the denominator. Okay. But this time, what's the difference there? What's the moral of the problem? Is this time x is going to negative infinity, so what can you say about the absolute value of x? So this time it has to equal to the negative of x, because x is negative, right? X is less than 0 as x goes off to negative infinity. So you make sure your grader sees that, you know that, and justify it. So now this becomes negative 1 instead of positive 1, because you have the absolute value of x over x. It's going to be minus x over x. So that's negative 1 this time. All right, tangent, inverse, sorry, arctangent is continuous, so we'll just pull that limit statement inside our continuous function. And now we evaluate the limit here. You know that all the terms that have a power of x in the denominator will go to 0 at the limit. Okay, so you're left with a minus. The negative is the negative 1, right? Square root of 12. over -2. So this time it's going to be inverse or arctangent at square root of 3, positive square root of 3, if you do the arithmetic there. So that would be pi over 3. So we get a different horizontal asymptote, right? This time, as x goes to -infinity, our function approaches horizontal line pi over y equals pi over 3. All right. Wow, I think, what else do I need to mention here? Maybe one more thing about limits at infinity. You might have to use squeeze theorem. So when do you, what do all these functions have in common? Inverse tangent or arctangent? What do all these functions have in common? Can somebody repeat that? Yeah, okay, that's true. Okay. What else do they have in common? That's relevant to squeeze. There. Oh, arctangent doesn't oscillate. But yeah, they're all bounded, right? So we know that sine always returns a number between negative and positive 1. So that's we say sine is a bounded function, right? It's bounded by 1. Right? And then cosine likewise is bounded by 1. An arctangent, as we looked at the graph of arctangent previously, we know that it's always a value between negative pi over 2 and pi over 2, right? So if you're anticipating and they tell you to use squeeze theorem and you see sine, cosine, arctangent, that's a good starting point. All right. So now we're going to look at this function and find a horizontal, take this infinite, find this infinite limit. I'm going to speed it up here. Okay. Right, so if you evaluate this directly, the problem is that you're going to get like something that goes to 0, except this cosine, it keeps oscillating, you agree? The cosine oscillates between -1 and 1, so it keeps oscillating. Okay. But so what we can do is look for the highest power of x in the denominator and maybe divide the top and bottom by it. So you would get 5 over x, you get cosine over x squared, and that's 10 minus 1 over x squared. So dividing the top and bottom by the highest power of x gets me that expression. Okay, and the squeeze theorem here at infinity is for this guy. Do you agree? Right. So how do we compute that limit? Well, you would reason that cosine of x is a number between -1 and 1. Okay, and then you want to get this function in the sandwiched in, right? Sandwiched in between two other functions. So it looks like we should divide everything by x squared, each part of this inequality by x squared. That way we get our function in the middle, sandwiched. So it's time to squeeze. So we take a limit as x goes to infinity. So all right. So we see that this limit is 0, and the other outside limit is 0, right? So the limit of the inside function, our function, must be between 0 and 0, right? Well, so it must be 0. Yeah. So therefore, the limit of our animal there is also 0. So that's the squeeze theorem. So you get that this is 0 minus, this is 0 by squeeze theorem. And then you get 10 minus 0. So this is an example of where you do have a horizontal asymptote, just so that you get a finite limit of 0. So y equals 0 would be horizontal asymptote. Okay. I needed to mention that. Also, you could use squeeze theorem even if it's not an infinite limit, right? So let's compute this limit. So this is going to be another example of squeeze theorem. It doesn't matter what the heck this is. Okay. Yeah, y equals 0 was a horizontal asymptote because this limit as x goes to infinity turned out to be 0, which is a finite number, right? Therefore, y equals 0 is a horizontal asymptote. Okay. All right. So, do you know where to start with the squeeze theorem there? Which factor is the problematic factor? As x approaches 0, which thing is the funky thing, and which thing acts as well behaved? Yeah. Well, sine squared, right, at 0 is 0, so that's perfectly.
It's the pi upon x squared.
Yeah, it's this thing, right? So as x goes to infinity, as x goes to 0, 5 over x squared goes to positive infinity, but cosine just keeps oscillating. So that's like the irregular factor. This is well behaved. Okay. So it looks like if we're going to use squeeze theorem, we should bound cosine, right? Cosine of who cares? I don't care how complicated the expression gets. Cosine always returns a number between -1 and 1. So then we would multiply everything by sine squared. Conveniently, I squared it, so we don't have to worry about multiplying by a negative, right? So I'm going to multiply each thing by this non-negative quantity, right? So sine squared multiplies everything, right? So that way we get our function, whose limit we want to find, in the middle. So yeah, you have 2 KGB agents going to the gulag, and you're always between them. You're going to end up. Yeah, and that's it. Now we take a limit. The limit as x goes to 0 of this left function is obviously 0 because sine of 0 is 0. And that's the same limit as the right function. So therefore, the limit of the thing that's always in between, at least locally, right, must be 0 as well. And you eventually will gain an intuition if you get into more math, right, where you say, well, this is bounded, this goes to 0, clearly that limit's going to be 0. So that's, again, by squeeze theorem. All right, so I did mention the squeeze theorem, so that's half of it, I guess. So. All right, we have to talk about continuity. Yes.
So for number 10, why did you put it in between 0 for the cosine, but for 11, you negative 1?
I'm a little confused. Are you referring to, let me just, referring to this?
Yeah, and then on 10, you did 0.
Uh-oh. I did?
You put it in between 0.
No, I didn't. I started off with saying cosine of x is between -1 and +1. Right? But it's after at the limit, the left and the right hand side of the inequalities. Yeah, they start with. All right. So what does it mean for a function to be continuous? Well, first of all, continuity is something that happens for a function at a point, right? It's a local phenomenon. And then if the function is continuous everywhere in some interval, then we say it's continuous on that interval. But using definitions, we can kind of consider the continuity at a point. So we say f is continuous at a point, at x equals a, say. If the following is true, at the end of the day, this statement kind of captures it all, right? Right? But we typically break that up into two parts, right? So the function must be exist at A. For me to even write that, the function has to be defined at A. Number two, well, for me to say the left-hand side of the statement, the limit has to exist. So we know that how to check limits. Limits exist if the limits from the left and the right exist, and they're equal to one another, right? So parenthetically, this means right, that we're going to take two one-sided limits, check whether those exist, and find whether they match. Right? So we know the limit in general will exist. The limit from the left and the right exists. Right? And finally, you check for that equality. Yeah. Right. So continuity. I mean, you can tell me why a function here is discontinuous, right? And so these are all graphs of functions which are discontinuous at A. So the first picture, let's call that picture A. Picture A, why is this function discontinuous at A?
It's not defined.
Yeah, not defined, for reason number one. That hole indicates the function is not defined at A. Graph B, we know that here the limit from the left, well, it exists. The limit from the right, it exists, but they don't match. So for reason number two, the limit doesn't exist. Graph C would be where the limit does exist. So as x approaches A from the left or the right, we get the same, the value of the function is approaching the same numbers, the same limit. So the limit exists, but the function at A is different than the limit as x approaches A. So that's reason number three. This is also reason, well, no, this is reason number two, right? And 1, 2, and 3. The function isn't defined there, and the limits don't even exist, right? You have vertical asymptotes. All right. So that's like your checklist. And intuitively, if all these three conditions are satisfied, well, for the function, these non-pathological functions, we're going to have a nice and connected graph, right? So you think of continuity as being a nice and connected. And differentiability, you can think of the graph being what? Nice and smooth. Yeah, so smoothness is like differentiable because a smooth graph, you can draw a tangent, a unique tangent, and continuity is like connectedness, nice and connected. All right. So let's quick, well, I'm not gonna lie. Let's look at this example. I was gonna say quickly, but you know. So you might get a piecewise function when dealing with, and then they also pull this cheap trig. Okay. So this is a piecewise function. So depending on the values of x, right, we use different expressions to define the functions. All right, so is each of these pieces continuous? Well, we know that polynomials are always continuous, right? They're continuous everywhere, so therefore they'll be continuous. Right, so this is continuous everywhere, including that interval from 2 to 5. This is a polynomial, this is a polynomial, degree 0. What about this guy right there? Is that continuous everywhere?
Within its domain,
It's not continuous with 5, but why don't we care? Because it's we only use that piece on x is greater than 6. So okay, so that piece is continuous on its domain. And this arctangent is also the only time that that this piece would be discontinuous would be if the denominator is 0, right? And that happens when the argument of arctangent is 0. So that would happen when x is 1, but that's not the case there. Okay, beautiful. So each piece is continuous on its respective interval. No, whatever, I can't erase that. So the only possible points of contention, right, would be the seams of our piecewise function. So at x equals 2, when we switch over from one piece to the other. So if we're going to check for continuity of our function, we should check at the seams there. So let's go to the checklist. At x equals 2. Is the function continuous there? Well, number 1, is the function defined at 2? Yes. So f of 2 is equal to 4, so it's defined, right? X equals 2 right there. So we would just use this piece. So 2 squared is 4. All right, number 2, does the limit exist? Well, to check that the limit exists or doesn't, we have to check the two one-sided limits for this piecewise function. So the limit as x approaches 2 from the left. So my x's are slightly smaller than 2. So here's x, smaller than 2. So we should definitely use the piece where x is less than 2, but close to 2. So that's the arctangent piece. Right, and this would give me, what's arctangent of 1?
5 by 4? No, wait. That's tangent.
Arctangent
Yes.
of 1.
5 by 4.
Yeah, it's pi divided by 4, so that's just 4. Okay. Now what about the limit from the right? So x is now going to approach 2, but this time from the positive side of the number line. So which piece do we use now? Well, x is going to be bigger than, right, 2. So that, but close to 2, so that should be, that's that interval. So x squared. Right, so piecewise functions, obviously you need to have the skills to know which piece to use, and you look at whether x is approaching number from the left or the right, and you pick the correct interval. So you get 4. Ooh, okay, the limit from the left and the right exist, and they're equal. Therefore, the limit in general, we don't no longer have to specify whether we're approaching x is approaching from the left or the right. This doesn't matter. The behavior of the function is the same on either side, so the limit exists. Right, it's equal to 4. Finally, you check that how the function behaves around 2 matches what the function actually attains at 2. So you check for that inequality, and indeed we have it. The limit is 4, which is what the function does at 2, right? So yes, right, all 3 conditions are met. So we say that f is continuous at 2. Okay. All right. So now let's look at you can consider x equals 5. Is the function continuous at 5. Why not? Yeah, the limit from the left, you would use this piece, right? So I'm not going to prolong the pain here. Right, since x is approaching 5 from the left, we know that x is close to 5, however, it's slightly smaller than 5, so that sounds right. So x squared 5. And the limit from the right, however, would be you'd use a different piece, which gives us a different number. Does it? Oh, yeah, okay, so this is the kind of quote-unquote cheap trick that I'm talking about, right? So this is 30 minus 5. So the limit exists. The limit from the left and the right are the same. So the limit exists. But they didn't define the function at 5 by simply, oh, crap. I hope nobody's getting sick online from from this going back up and down like a roller coaster. So the problem is right there, this thing, right? So here, this is only when x is strictly less than 5. The next piece is only used when x is strictly greater than 5. This tells you doesn't tell you what to do when x equals 5. So this piecewise function is not defined at 5. So it's reason number 1. I thought it was reason number 2, but I'm wrong. So f is not defined or at 5. So f is not continuous there. Right. So you can kind of stop, right? And even though the and by the way, what does it mean for a function to be for a discontinuity to be removable? What does it mean for a discontinuity?
Oh, that you can build a hole and then it'll be continuous.
Yeah, if you define your function at a point or redefine it so that you plug the hole, then it's removable. So if the limit exists, it's a removable continuity. So here, the limit exists, therefore it's a removable discontinuity. It's a discontinuity because the function is not defined there. But since the limit exists, we can simply say let function at 5 equal to this limit, and that's how you remove that discontinuity. All right. All right. Well, and you can check at 6, right? X equals 6. The function would be discontinuous there. F is discontinuous at 6. Maybe I should write a complete sentence. I'll let you check that. Because even though the function at 6 is defined to be 30, and the limit exists as x approaches 6, I believe the limit would be 31. Since the limit does not equal the limit as x approaches 6 of our function does not equal the function actually does at 6. It's for reason number 3, right? The function is not discontinuous there. I think we should do one more. By the way, I don't know. It's like it's 3. So I'm going to continue because I'm recording this. But if you need to be somewhere and to go, obviously you're free to go. So, okay. Yeah.
How many topics you have left that you were thinking about discussing?
Well, I have another continuity. I could find values of a and b so that the function is continuous everywhere. So a piecewise function like this, but just a slightly different flavor. We're going to talk about the limit definition of derivative and use that to compute some derivatives and find tangent lines. And then some basic differentiation rules. So that's after the limit definition of derivative, to actually compute some derivatives, including quotient rule, product rule, and maybe derivatives of trig functions like sine, cosine, secant, tangent, cosecant, cotangent. And then quotient rule, I already said quotient rule and product rule. So that's a lot of topics. But if you need to go, don't be shy, because I understand. 2 hours is too much. But anyway, I'll have this recorded. So even if there's somebody here, I'll keep talking. So, all right. All right. So what's next? What do we? Oh yeah, piecewise function. Find values of a and b. What number are we on? This one. And good luck on the exams, by the way. Okay, so now we're gonna, and Kurti, if you need to, Kurti, if you need to leave, go for it. Thanks for helping out. I don't know how long you plan to stay here, but officially the exam review was till 3. Okay. All right, so here we're gonna find values of a and b to make this function continuous everywhere. And I'll write down the function in just a second. All right, so here's our piecewise function. Yeah. Yeah. No, that's correct. Yeah, I'll do that. Yeah. I could have, but I wanted to keep it simple. Just have a simple trig function divided by x squared. So there it goes. Cheesy, that one. We're simply going to connect the pieces by a line, so I'm pretty sure we could do that. And a little too complicated, perhaps. But anyway, we'll just quickly do this because we computed the limits. So this is for x smaller than 2. This is for x is between 2 and 5. Inclusive. And this is for x is strictly greater than 5. All right. So now each piece is continuous on its respective interval, as you can check. Okay. So the first piece would only be discontinuous at x equals 2, but we wouldn't be using that piece anyway when x is 2. The second piece is continuous except at x equals 5, right? But again, this piece is not used for when x is 5. It's only used for x is strictly greater than 5. All right. So we just have to guarantee continuity at the seams where we switch over from one expression to the other. So the x equals 2. What's the limit as x approaches 2 from the left? Which piece would we use? Well, the one where x is slightly smaller than 2. So that. So computing that limit, it's a special trig limit, and you would get 4. Right, because all you would do is just introduce a factor of x plus 2 on top and bottom.
multiply the top by x plus 2, multiply the bottom, so that you get the what's inside the sine function. You know, these guys now match, so we get to use our special trig limit and get 2. All right, so the limit from the right, yeah. So this time x would be slightly bigger than 2. So here's 2, here's x. It's going to be slightly bigger than 2. All right. So we would use our the line part of that piecewise function. Okay, so you get 2a plus b, right? That's just a polynomial, so. All right, so this tells me that, you know, we need the limit from the left and the right to agree for the function to be continuous. So we're going to have from the left and from the right, and this also happens to be the function at 2. So that's one equation that will help us solve for A and B. But that's 2 unknowns, but only one equation. So there's obviously another equation that comes from what happens at 5, right? X equals 5. So we're going to have the limit as x approaches get 4. Oh, so somebody mentioned in chat that as x goes to 2, x plus 2 will go to 4. Thank you. That's a good point.
I have a quick question.
Yeah.
What do you thought x plus 2 on the outside?
Yeah, so we got that because we're trying to use a special trig limit, and we see that we have, inside our sine function, we have x squared minus 4, right? So on the bottom, we want to see exactly x squared minus 4, so we can use a special. So we anticipate that if we were to multiply the bottom by x plus 2, the conjugate, you would get x squared minus 4. So we multiply the top and bottom by x plus 2. It's the whole thing, anticipate, you know, you can multiply by conjugates to force difference of squares, to get rid of square roots, to introduce, like if you have a perfect difference of squares in the sine function, you need that in the denominator. So, all right, so then the limit, oh yeah, that's, what was it, 5? Yeah. So limit as x approaches 5 from the left, we would use the piece that's appropriate. X is slightly smaller than 5 as x approaches 5 from the left. So that looks right. So ax plus b, the middle piece. So you get 5a plus b. Now x is going to approach 5 from the right as well. So this time you'd use the last piece where x is bigger than 5. And yeah, I'm not going to, this is evaluating limits, but you can see how they can like take several concepts that they're testing into one problem. But here you have to multiply by the conjugate, and you get that this limit is equal to, does anybody know? If you multiply the top and bottom by the conjugate. We would get that this that gives you x minus 1 minus 4. Yeah, those would cancel. Sorry, I'm going to skip that algebra. And evaluating the limit directly, we get 16. Okay. So now we see that the function, the limit from the left and the right agree. They have to agree to have continuity. So this time you get 16. The limit from the right must equal the limit from the left. Not only that, the 5a plus b is actually what our function does at 5. So now you have 2 equations, 2 unknowns, you solve them using your algebra skills. So 2a plus b equals 4. On the other hand, 5a plus b equals 16. Just subtract one equation from the other, and you get 3a minus b plus b is 0. 16 minus 12. So a would be 4. Okay. So, and then if a is 4, then what is b? So that would be negative 4.
So there you go. To make sure the function is continuous, right? So we use the line kind of to stitch all the pieces together so the complete graph is nice and connected. A needs to be 4 and B needs to be negative 4. Okay, so that's another flavor of the piecewise continuity problem.
I have a quick question.
Yes.
So for that, do you put 5a minus 1b or?
Okay. What are you talking about these?
Yes.
What's one?
Like the next equation?
This one?
Yes. What
Yes.
is that after 5a?
Oh, it's plus B.
Plus
Yeah.
b. Cool. Thank you.
Yeah, you're right. I mean, I'm communicating here. I should be less sloppy. That's a. Yeah.
Thank you.
All right. So now we're going to use the limit definition to actually compute some limits. So, do you remember what the idea for the derivative is at a point, say, let's say A? Remember the picture? Right, so we have some function here's x equals A, and then we have the function at A. And then we take a value of x somewhere else there, plug that x into our function. And then you say, well, that if we know how to find the slope of a line that contains 2 points. So that slope is the change in the y values, would be f at x minus f at a. And then divided by the change in the x values, so that the x minus a. And then what's the calculus part of this, right? Well, as we take a limit, x approaches a, our secant line is then going to become a tangent line, so it's just going to graze the graph of our function. So at the limit, our secant line becomes tangent line, and the slope of the secant line becomes the slope of the tangent line at the limit. So that's one way to look at that. And we had an equivalent way where we have the derivative of the function at an arbitrary value of x. So now the fixed point is x, and instead of, so now to say when we take a point near x, we're going to say x plus small change, right? So plus h gives us the point nearby. X, so the change in the y values would be the function at x plus h minus the function at x. And then divide by the change in x values. Well, one x value is x plus h, the other one is x, so you just get h. And this time, to say that one point is approaching the other, approaching x, that means h has to go to 0. All right, so these are two equivalent definitions, right, for a derivative or instantaneous rate of change. Right, so now let's find the problem. Yeah, I'll just make one up, I guess, going off of this. Okay, I got it. Later.
Thank you.
Yeah.
That was helpful.
Good. So this is now problem number 14.
Only problem 14. Wow.
Yeah. Oh, that looks pretty evil. All right, so do you guys want to find the derivative of this function at
0.
1 at 1. So find, okay, this problem could be stated a couple of ways, right? What is it? So instantaneous rate of change. Somebody help me out spelling. Oh yeah, like stan, okay, instantaneous. All right. Rate of change.
And you're supposed to be tutoring as math.
Huh?
You're supposed to be tutoring us.
Oh, I know, but I mean, I don't know. What can I say? I'm sure I could find some clinical excuse if I wanted to, but.
Fair enough. English is hard.
The instantaneous rate of change of f at x equals 1. All right. Another way would be to simply say, find the derivative of the function at 1. Okay. Another way to say that is to find the slope of the tangent line or when or at x equals 1. Right? So different ways of just saying that. And we're going to insist on using the limit definition. So f prime at 1 is the limit. Okay. And we'll use the first kind of way of writing that. So it's going to be the change in the values of the function, the function at x versus the function at 1. And then the change in the values of x, so x minus 1, and we're going to take the limit as x approaches 1. All right, so what is the function at x? Well, it's written down, so that's the function at x. What's the function at 1?
1/3.
Right. And if you're using a limit to get a derivative, then you're going to get 0 over 0, right? So we need to do some sort of algebra, and so this is as I don't know. Do they really want to get more complicated than this, right? So what can you do?
Take the multiply by the conjugate.
Yeah, sure. Yeah, I would have first find a common denominator because it's both a question of fractions and square roots. But you're right; you can just multiply by conjugate. I'm not going to do that. I want to find a common denominator first. Well, it is. Yeah. Find a common denominator, so you get 3x minus the square root of x squared plus 8, all divided by the common denominator, which we got by simply multiplying the two individual ones. So that would be 3 all divided by x minus 1. So then dividing by a fraction is the same thing as multiplying by reciprocals. In the denominator, we're going to get 3, x minus 1, and square root. Did I miss something up or no? Is that good?
I think you have to use conjugate after this.
Yeah. I'm just checking my works, arithmetic, algebra. Okay, so now I multiply by the conjugate, right? So we're going to multiply the top and bottom by the conjugate. So that's to get rid of the square root. Okay, in anticipation of taking a limit, eventually we know that we don't need to multiply out the junk in the denominator. The idea was to simply force the difference of squares when you multiply the factors in the numerator. So we get the first term squared minus the second term squared. So that gets rid of the square root, but remember that minus applies to everything there. So I'll use parentheses. Excuse me?
Why did you go from 1/3 to 3?
Oh, so this was when I found a common denominator here. So here I multiplied the top and bottom by 3. And for the 1/3, I just multiplied the top and bottom by the other fractions denominator. So I multiplied the top and bottom by x squared, square root of x squared plus 8. Is that okay? And once you have that common denominator, you get the result from there. All right. All right, so we simplify. God, I hope they did this right. Oh yeah, okay, it feels right. So you get 8x squared minus 8. Right, so, okay, fractions and square roots, and now also polynomials, right?
We have to put the 3x plus square root of x plus 8 in the denominator.
I'm not sure what you mean.
You multiply by 1, remember, so you need to add the bottom part of the 1 to the denominator.
And
3x plus square root of x squared plus 8. We didn't carry it to the denominator.
they didn't carry something into the denominator. Yeah, you can come up here, that would be great. I don't see any
You
mistakes.
forgot to carry this into the denominator.
Oh, yeah, very good. So, yeah, okay. You know, that's, it's not like I haven't seen graded exams where this is exactly the mistake people make.
And you're supposed to be tutoring us in math, man.
Yeah, I know, but you know. Okay. So then, 9x squared minus x squared, factor out an 8. X squared minus 1 can be factored into the product of conjugates. Oh, I can't believe that's not erasable. That is the weirdest thing, in fact. There you go, just a little lag. I know, this is awful. I'm glad I have a degree on taking more tests. Okay, so x minus 1 divided by x minus 1, that cancels. Now we evaluate the limit correctly. So you get 8 times, this goes to 2, and we get, that goes to square root of 9 is 3. Where does this go? This goes to 3 plus 3, so 6. All right, so this is going to go to 4 over 27. Okay, so that's the slope of our tangent line. The derivative of our function at 1 is this numerical value. Okay, beautiful. Okay, so we will not do the one where we want to find the derivative as a function of x, because that's the same algebra. So we'll do, well, I had it written down. There you go. Anyway, but that was pretty good. That was pretty inclusive. It had like square roots, fractions, and factoring polynomials to eventually be able to evaluate the limit. Okay. Okay, so next we're going to use some differentiation rules to find the equation of the tangent line. So we're going to use power rule. So x to the power differentiated. We all know this one. You bring down the power, subtract 1 from the old power to get a new power. We're going to use the product rule, where you just take turns differentiating one factor at a time. We'll use the quotient rule. So I don't know how you memorize that, but it's just you have a subtraction. You're welcome, and you differentiate one factor at a time. You differentiate the top first, so u prime, and then divide by bottom squared. We have a constant times a function differentiated, just leave the constant alone. However, what's the derivative of a constant? 0, right? Its rate of change is 0, it remains constant. Are those all the rules? The derivative of the sum is the sum of the derivatives. So if you have f plus g minus g, just differentiate term by term. So
There's also the natural growth one, the e to the x.
oh yes, so the derivative of e to the x is itself. So this is why you'll see this function from the rest of your scientific career, right? So differential equations and stuff. Okay. All right, so now let's look at this function and try to apply all these rules in order to find the equation of a tangent line. All right. Okay, so let's just look at some of the terms. Right? So 5 over 2x squared, just to anticipate what's going to happen. How do you differentiate that? Well, we want to think of this as constant, okay, and then times a function of x, but in order to use power rules, remember this power rule works for any power, right? So we want to think of that as mature calculus students as x to the negative 2, so that's just easier to apply the power. So we have a constant, leave it alone, this is different than multiplying a function, and then we have the derivative of x to the negative 2. So we drop the exponent in front and subtract 1 from the old exponent to get a new one. All right, so that's negative 5 times x to the negative 3. All right. What's the derivative? Well, okay, great. So the derivative of our function would just be derivative of the first term, which we computed, plus the derivative of the second term. All right, and if you have square roots, what's the way we're going to think about square roots? Okay. It's fractional powers, right? The cube root would be a power of 1/3, fourth root would be power of 1/4, and so on. In general, the nth root. And we do this, of course, because you want to use the power rule. Again, this works for any power, fractional, negative, positive, rational, irrational. So we're going to write the square root as x to the half. And here, since you're not using chain rule, I kind of messed up there. Let's just think of that as e to the negative 1 times e to the x. Right, so that's properties of exponents. And we have to differentiate this, right? So what rule do you want to use to differentiate this, let's say at the outset? What's your first kind of impression? Well, it's a quotient, right? Top and bottom, numerator, denominator. So we'll use quotient rule.
Chain rule is not part of the exam, right?
Yeah, no, it's not.
It's not.
I mean, it's good in theory, but I don't know.
Well, anyway, the professor said through sections 3.3. That's all I know. So I believe chain rule is on 3.4 or something.
Yeah, so if we use that, our marks will be counted. If we use that, our marks will be counted.
I mean, in theory, it shouldn't be, because we technically learned it in class.
So we'll take the top and we'll differentiate that first according to quotient rule. I'll just write prime for now. I'm not actually differentiating.
Could you check e to the 1 out right now, because it's a constant?
Yeah, I could, but I don't want to. I want to let my grader know that I know what the quotient rule looks like. So I'm just going to write out. I'm not without differentiating, right? I'm just going to write the what the quotient rule will tell me, even though I'm not doing it yet. So differentiate the top, so that's the prime, times and leave the bottom alone, minus per formula. Leave the top alone. and multiply by the derivative of the bottom. Right? So even if you just take the time to write that, if you think about what's going on there, is that your grader sees that you know this. So if you make a silly mistake past that, your grader will be more forgiving. Okay. And then divide by the bottom squared. All right. Okay. However, to differentiate, I'll highlight this in yellow, differentiate this factor. Okay, let's do that on the side. What rule do we want to use? Well, that's a product, is it not? So product rule. Here we have, let's say that's U and that's V. So that should be according to the product rule. I'll come back to that. So it should be U prime V plus U V prime. Okay. So we're going to have x to the half differentiated. And then we leave this second factor alone, plus leave the first factor alone, differentiate the second. Okay, and what's the derivative of x to the half? Well, power rule. So bring down the exponent. Subtract one from the old exponent to get the new one. Okay, and then differentiate this factor. So we have to remember that e to the minus 1 is just a constant, right? So we'll leave the constant alone and we differentiate e to the x, which is equal to, e to the x is that function that's equal to its own derivative, except maybe for the constant function 0. Yeah. All right, so then we could rewrite that if you like. You know, this is e to the x minus 1 over 2 times square root of x. And that's square root of x. We don't have to. Aesthetics really. Okay. All right. So now the highlighted. Now remember, we're going to be evaluating the specific at a specific point. Did I mention that or no? I didn't mention it. So I think at x equals 1, right? Oops, I forgot the rest of the product rule. All right. So unfortunately, that's just the derivative of the highlighted yellow part, right? Okay, and then we have the next factor, which... Okay, so at this point, I'll interrupt and say that I made a mistake. So this factor should not be here. Okay, so since this is messy anyway, I'll just go ahead and quickly start maybe somewhat from the beginning. So let me just pick up from there. All right, so we're computing the derivative of f. And we know that you can differentiate term by term. Differentiate the first term plus, and then differentiate the second term. I'll go ahead and write the square root as a power of 1/2. So we can more easily apply the power rule when we actually differentiate that factor. This guy, we don't want to be using chain rule yet. That's in section 3.4. That's okay. We're going to take e to the x minus 1 and use properties of exponents. And think of this as a constant, namely e to the negative 1, or 1 over e, times e to the x. Okay, so we already determined that the derivative of the first term is simply negative 5 over x cubed, using the power rule. Okay, and the derivative of the second term, well, we see that we have ultimately a quotient, so we will apply the quotient rule. So we will go ahead and write that out, and we won't actually differentiate. We'll just write out the form of the quotient rule here, so letting our grader see that we do know the quotient rule correctly,
even if later on we make a mistake like I did. Okay, now I'll go ahead and focus on differentiating the two factors, the numerator. So here we're going to use the product rule, where the first factor, let's say u, is this square root of x, and the second factor is this constant times e to the x, our exponential function. So the derivative of x to the half, using power rule, bring down the power, subtract 1 from the old power to get the new exponent, and then the derivative of this constant times some function of x. We know that we leave the constant alone and multiply by the derivative of our function. Okay, so we leave the constant alone, and the derivative of e to the x is e to the x. So that takes care of this derivative. So now we're going to go ahead and, so now the derivative of x cubed plus 1, differentiating term by term, power rule, and the derivative of the constant is 0. So now we're going to pull all the pieces together and write out the full derivative here. Okay, so we have our derivative and our function, and the original instructions are to find an equation of a tangent line at x equals 1. We need a, so we're going to use the point slope form of a line. For our point, we need to use the original function because we have the x value is 1, and the y coordinate of our point of tangency would be the function, the original function evaluated at 1. So the y coordinate is, so the function at 1 is equal to 3. This is our point of tangency. And then, of course, to get the slope, that's just the derivative of the function at 1. So let's go ahead and evaluate this derivative at 1. So we get that the slope is -5. Finally, we plug in the point and slope into the point slope form for the line. And if we must, let's go ahead and write that in slope intercept form. And so this is at the end of the day the equation of our tangent line.
So if they asked you where does the function have horizontal tangents? How do we approach this problem?
Find the derivatives at equal to 0.
Yeah, exactly. Very good. Right? We know that the slope, horizontal tangents are tangents that have slope 0. Horizontal lines have slope 0. And we know that the tangents, the slopes of tangent lines are given by the derivative. So you have to compute the derivative and then figure out for which values of x that derivative is 0. So that's our approach. So here I was going to use the limit definition. You can practice, but I'm just going to use differentiation rules right now at this point. So that looks like a quotient. So I'll use quotient rule. Differentiate the top, leave the bottom alone, minus the top times the derivative of the bottom. And does anybody know a good way of remembering that? Because some people have this little low high thing. I don't know how people memorize that little rhyme scheme.
Low, high, high, low.
Yeah. So you can memorize that, but you can't like memorize what the quotient rule looks like on a piece of paper. It's so weird to me. It's interesting. But can you say it louder for the audience online?
Low, high minus high, low, all over low, low.
Did everybody catch that? Well, all right. Okay, so actually, so I just wrote the structure of the quotient rule, and I'm just gonna differentiate. Yeah, just the key is to remember there's a minus in between, and then you first differentiate the top, the first thing, if you will. All right, so simplify. That gives me x squared plus 6x, all divided by x plus 3 squared. All right, so now we set that equal to 0 and factor. You know, there's going to be a follow-up question here. Do you know what it is? Okay. But anyway, so solving for x, we see that x could be 0 or x could be -6. Okay. That would make the derivative 0. Right. Okay, so there you go. That answers the first question. Where does this function have horizontal tangents? Notice that these values of x both are in the domain of the function. So the domain of our function is all numbers except the one that would make the denominator 0. So we're going to exclude -3 from the domain. Thank you, Curdy, for writing that down in chat. Okay. All right. Does this function ever have vertical tangents?
Yes.
Where?
X equals -3.
No, it doesn't. Why not? It's true that vertical tangents means your derivative would be plus or minus infinity. So, right? Yeah, exactly. So to have a tangent at a point, your function has to exist there, right? So that's a trick question. No, it doesn't. Even though this expression goes off to infinity, right, as x approaches -3, at -3 the function of it's not defined there. It doesn't even exist there, so you can't talk about tangents of the function.
So vertical tangent is just straight up impossible.
For this function, yeah. We could cook up some examples where, let's say, the domain of the function is all real numbers, right?
Okay, so in that case, a vertical tangent is possible, just not for this function.
Yeah, exactly. In general, it's possible. So let's say that this is fudge. Yeah, I would have to be careful. You know what? I'm not going to give an example because I could really mislead you. Right? Anyway, so that was a problem. And the last thing we should talk about is, of course, the derivatives of trig functions. So sine, derivative of sine, derivative of cosine. Okay. Oh.
All right, I gotta go now. I'm leaving it to online kids and everybody else here to point out his mistakes.
Okay, great, awesome. All right. Have a good one. All right. So, and then we have the derivative of tangent, the secant squared, which if you ever forget, what's the way to derive this derivative? Well, you just use the fact that tangent is sine over cosine, right? And then you would use quotient rule. So derivative of sine times the bottom minus high, I'll try this, high d low, which is a negative sign, derivative of cosine is negative sine, divided by low or low squared, right? Anyway, that gives you cosine squared minus a negative sine squared. So that's you get to use your Pythagorean trig identity. And so you get 1 over cosine, and what's another word for the derivative? So what's another word for the reciprocal of cosine? Secant. So this is secant squared. All right. So you can, if you ever forget, right? And by the way, what's the derivative of secant? Again, you can use quotient rule, right? Because it's just 1 over cosine, so it is a quotient. But it turns out to be secant tangent. And then the kind of related one, what's the derivative of cotangent? It's going to be like, what's the analog of secant squared, right? That would be cosecant squared, but it's negative. Forget these. So. And the derivative of cosecant is negative. That's me. I didn't bother to disable these buttons when I started. So that would be the derivative. Negative cosecant times cotangent. So you can see there's some sort of kind of skew symmetry going on here with these, all these derivatives. They look similar. They're off by a negative. Okay, so those are the basic ones. So let's find the equation of tangent line to this function. So this is number 17. Okay. At x equals pi. All right, so since we need a line, right, if they had just asked for the slope of the tangent line, you could just go ahead and differentiate. But since it's a line, we also need a point for on our line. So the point would be when x is pi, what is the y corresponding y value? What's tangent of pi? What is tangent of pi?
Zero.
Yeah. And what's secant of pi? Secant is 1 over cosine. So cosine of pi is -1. So yeah, yeah. All right, 1/2, right? Pi and a half. All right, so now we're going to find our slope, and we know that that's the derivative of our function at pi. And right, they wouldn't ask you to use the limit definition of this. So we just need to use the rules for derivatives, which obviously is a quotient rule. So let me try this, okay? D high, right?
Low D high.
Oh, low, so the denominator goes first. Okay. And then D high means the derivative of the top, I believe. So the derivative of 1 plus the derivative of that's right. So low D differentiate high minus high, so leave the top alone. D low, so differentiate the bottom. How do you people memorize this stuff? The low squared or low. Right. So then we just have to use our differentiation rules. And I'm not going to simplify because we know that we're finding the derivative at a specific value of x. Derivative of tangent, secant squared. Derivative of secant is secant times tangent. All divided by low squared. Okay, and then we evaluate this specifically at pi. So again, you know your unit circle. You get 2, 1, 1. You get 2 squares. Okay, I'm going to trust that you can figure out how to evaluate that. So the slope is 1/2.
There you go. So now we use the point slope form of a line. Y minus the specific y coordinate on our line, slope, x minus the specific x coordinate, and I guess write in points, slope intercept form if you must. Okay. Slope is a half, the y-intercept is 1 minus pi over 2. And maybe for practice, I won't do it, but maybe you want to try something like, right, instead of tangent and secant, maybe you want to work with cotangent and cosecant. Similar problem. Find the equation of the tangent line at x. Well, it can't be pi, right? Can it? Yeah, it could be pi. No, it couldn't be. Why couldn't it be pi? What's wrong with the... Well, pi is not in the domain of the function, right? Because cotangent is the same as cosine over sine. So if I let x equal pi, I would be divided, sine of pi is 0, so you'd be dividing by 0. So I have to make something else like x equals 3 pi over 2. Right? Yeah. So you can try that one. So this one, how would you approach this simple problem? This would be the easy one, right, on the test. Yeah, so you've probably seen something like that on the homework, but what's this problem all about? The problem is all about, well, would we want to use the quotient rule, first of all? You know, why don't we have to? Well, because there's exactly one term in the denominator, right? So we can easily just divide all the terms in the numerator by that single term in the denominator, simplify, and then it's just an exercise in using these two rules, right? The derivative, or this, let's say one rule. The derivative of a constant times x to some power, leave the constant alone and use power rule. Right? So we would, x to the 7, let me write it out. And how do we want to think of this? Because I know that's ambiguous, but what I meant to write is the cube root of x to the power 7. So we're going to think of that as x to the power 7 over 3. Is that supposed to be x squared? No, it's supposed to be x cubed. All right. Great, great. So now we're going to simplify using properties of exponents. What's 7/3 minus 2? It's 1/3. All right. All right, so this is all pre-calculus, right? Just you know, tidy it up before we prepare this before serving it here. So f prime, power rule. What's the derivative of a constant times x?
Just the constant.
Yeah. And what about the next term? We have a constant that we leave alone, and then use power rule for the derivative of x to the power 1/3 and negative 2/3. Thank you. And what's the derivative of a constant?
0.
And what is, and then here, yeah, power rule works for negative exponents, so bring down the exponent, subtract 1 from the old one, exponent. Cool.
And I was going to do a fine equation of tangent line, blah, 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 but you know, I think you know. Oops. Right. Awesome. So that's just an exercise, my power rule really. Knowing to do the algebra first. All right, and maybe we should make this the last one because it is 3:58. All right, so you've seen these problems. It's really a homage to physics, right? Which, but of course, calculus and physics have nothing to do with anything in common, right? So it's a true and false question. Am I being sarcastic or not? I'm being sarcastic. Like Newton, right? Calculus physics. All right, so this is the, this is the whole, here's the height of some object at time t. Okay. So this is the vertical position of a function or height of a function at time t. Okay, so this is position. And so if they ask you about velocity, what do you have to do? What is velocity?
The derivative of the position.
Yeah. Velocity is the distance divided by time, right? So in terms of calculus, it's the instantaneous rate of change of position with respect to time. So we're gonna, to get the velocity, we just have to compute the position, differentiate the position, so h prime. The derivative of position with respect to time gives you velocity. And by the way, they probably wouldn't use a 5 over here. What do they typically use if they're dealing with like projectile motion, 4.9, or if you're 30 or 16, or like, so 9.8 meters per second squared is acceleration, or 32 feet per second squared. So that's typically what they use. All right, so the question is, what's the initial height? This is a freebie, guys. It's the initial height. What does that mean?
You plug it into the equation of that f of t, like, or it's like f of t minus f of divided by x minus t.
Yeah, the initial just means at the starting time, right? So let's say t equals 0. That's when we start a stopwatch. That will just give you 10. So this number just gives you the initial height. So if they had reversed the problem, they say that we throw an object from 10 meters high. That would be the initial height. What's the initial velocity? Well, initial, let's just say, means t equals 0. So it's the velocity at time 0. Right, so evaluating the derivative at time 0, and I messed up, this is t, we get 5. So the number that multiplies the t term, right, is the initial velocity. And so if you throw up an object from 10 meters high, and you throw it up at an initial speed of 5 meters per second, that's where that initial velocity would go, in front of the t. And, okay, what else do we need to know? Oh yeah, so the real question though, of course, is what is the velocity of the object when it hits the ground, when it's about to hit the ground? That's the real question. So I should, if I should have made the problem clear. This gives you height above ground level, position above, relative to the ground, above ground level, right? So I'm sure they'll be clear if they make a problem like that. So when they say to hit, when you're about to hit the ground, what's your height, right? Relative to the ground, 0. So that just means h is 0, So can you compute your velocity when height is 0? Or is there something missing?
Can you try like the T where
Yeah, that's exactly right? So before we calculate the velocity when you hit the ground, we have to figure out what time we hit the ground, right? At what time do we hit the ground? So that's the that's the question that we have to make ourselves. At what time do we hit the ground? Right, that's the, if they're nice, they'll ask you that first, but what if they're not, you know. So that's to say, at what value of t is the height 0? And that gives you a quadratic that you can solve for. So this is what you'll be doing in physics 1 a lot, right? Right, so that's a quadratic in t. So we know that we can use the quadratic formula, or we can factor. Can we factor? I'll use the quadratic formula. How about that? Also, my 5 is equal to 3. So. All right, so using the quadratic formula, we get. I gotta write it down for review. So. Okay, right. Quadratic formula helps you solve for the zeros of the quadratic. So minus b plus or minus root b squared minus 4 times a times c, all divided by 2a. So what is that? 20, 10, 200, 225. And the square root of 225, I believe, is 15. Okay, so you either get 20, so 5 plus 15 divided by 10, or you get 5 minus 15 divided by 10. So, right, do both of these answers make, I guess, do they both make physical sense? Well, yeah, right. It's just that it's kind of like if you had gone in the past, a second before, you would have been at the ground level. At time 0, you're a height of 10. And then at time equals, the positive time is what you want. At time equals 2, you're hit the ground. Right? So we would just choose the positive answer. Okay. So now that we know at what time we're about to hit the ground, we can compute the velocity at that time to answer the original question. So the velocity was 10 minus 5t when t is 2. Sorry. Gives you, does that sound right? Oh, 5 minus 10t, not 5 minus 10. Okay. 5 minus 10t when t is 2 gives you negative 50 meters per second. Yes. Right. All right. Well, and if they had asked for speed, what would your answer be? I don't know if they get that technical. What would the answer be for the question? What's the speed? What is it?
15.
Yeah, it's the speed is the absolute value of velocity, right? Velocity could be plus or minus depending on which direction you're going. Plus for up, minus for down. Okay. Wow. Yeah. Thank you, everybody. That's it.
Thank you.
Thank you.
Yep. Good luck.
Do we put the value of the derivative of each of
Yes. So the velocity at t equals 2 with z of 2. And velocity is 5 minus 10t, and you evaluate it in t is 2, you get 5 minus 20.
the derivative of
Yeah, this is the derivative of position. We already computed that. Let me scroll up to show you. So we computed the derivative of h over here. So that's our velocity, 5 minus 10t. So that's what we used.
And we found the value of t from the original function.
Yes, because we needed to know, before answering the question, what's your velocity when you're about to hit the ground, we have to figure out the time at which we were about to hit the ground. So we knew that ground level means your height is 0. So we had to go to the original and say, when is h equal to 0? So what value of t is h equal to 0?